Okay, so rarely am I lucky enough to get to like put the main theorem on the first slide, but here's like, which is bad actually for everyone coming in late. But okay, so here's the main result. Any polynomial size linear program for max cut has integrality gap of 1/2. For max 2 set has integrality gap of 3/4, and for say max 3 set has integrality gap 7/8. This is the main result. So let me just point out that these are the integrality gaps achieved by the most standard basic LP that you would write down on day 1 for these problems. These are also the approximation ratios you would achieve by just random assignment to the variables. In the case of max 3 set, by Johann's work, we know it's NP hard to approximate within 7/8. So in particular, if P is not equal to NP, it implies this result, but this will be unconditional. And then also for max cut and max 2 set, we know that actually Gomez-Williamson gives something better than 1/2 and 3/4, right? So this shows that, I mean, there's a simple quadratic size semi-definite program, for instance, for max cut that achieves much better than 1/2, but any polynomial size linear program can do at best 1/2. And okay, and actually this holds not just for polynomial size, but lower bounds of n to the log n, approximately, on the size of the linear program. I didn't tell you what a linear program is, obviously, because we didn't prove P is not equal to NP, so there's some caveat. Okay, and the main technique is maybe a bit surprising initially, that for max constraint satisfaction problems, actually polynomial size linear programs are exactly as powerful as a constant number of rounds of the Shirley-Adams hierarchy. So, and then of course all these bounds follow because we know very strong bounds for Shirley-Adams. Yeah.
So are you making any assumptions here on what the variables stand for?
Yes. So we'll get to it soon. So in particular, it's known that linear programming is P-complete under sort of various notions of reduction. So if you could really prove this for any linear program, then you would be saying that NP doesn't have polynomial size circuits. But on the other hand, I mean, am I solving max cut by linear programming if I first reduce it to using my magical reduction to weighted bipartite matching and then use an LP for weighted bipartite matching? I mean, you probably wouldn't call this linear programming. So of course we have to be more specific.
Yesterday your open problem was how to improve this into the log n.
It had a log n, but it was completely unrelated to this.
There was some LP though.
Yeah, it's a good problem. We can talk about it, but it's somewhat unrelated. Okay, so let me tell you about a very incomplete history of linear programming lower bounds. They basically come in sort of two strains. One is work on these specific linear programming hierarchies, like the Lovász-Shriver lift and project hierarchy or Shirley-Adams. This sort of, considering these sort of systematically for approximation problems, this was really kicked off by Aurora, Bolobash, and Lovász in 2002, trying to understand what are the integrality gaps for increasingly more sophisticated linear programs. And just as a reference point in everything I say, these LP hierarchies, they have rounds. And as you increase number of rounds, of course, they become tighter and tighter until at n rounds, they really equal the integral Hall. But you should think about the R round relaxation as size n to the order of R. This is how to compare rounds and size. So what do we know here? We know lots of things. There's been a lot of work. Let me just focus on max cut. So we know that max cut has an integrality gap of 1/2. So Schenbeck, Trevisan, and Tulsiani proved that in Lovász-Shriver, for a linear number of rounds, the gap is still 1/2. I should mention that Shirley-Adams is strictly stronger than Lovász-Shriver. So results for lower bounds for Shirley-Adams are stronger than Lovász-Shriver. Fernandez de la Vega and Mathieu proved that any constant number of rounds of Shirley-Adams still has a gap of 1/2 for max cut. And then after that, Charkar, Makarichev, and Makarichev actually proved that n to the epsilon rounds of Shirley-Adams still has an integrality gap of 1/2. There are some quantifiers there, right? To get 1/2 plus epsilon, you have a lower bound against n to the c of epsilon. Okay, but rounds. But actually, quite strong lower bounds. So this is one model where we have actually very kind of strong lower bounds for very specific families of linear programs. And then there is this other line of work based on extended formulations that was started by Yannakakis in the 80s, where he showed, I'll say what this means in a second, that every symmetric linear program for TSP has exponential size, has to have at least exponential size. And also so the same thing for perfect matching. Okay? And then it was open whether or not the symmetry assumption was necessary, and very recently in this beautiful work of Fiorini et al., they actually show that any polynomial size linear program relaxation for TSP has size at least 2 to the root n. Okay, so let me tell you in this setting what linear programming relaxation means. So here's the idea of an extended formulation. You have some polytope in Rn, okay, which is possibly very complicated. So for the case of TSP, this will be the convex Hall of all the integral tors of the complete graph. Okay, so it's known that this thing is very complicated in the sense that it has you need like n factorial defining inequalities sort of to get this polytope. It has many, many facets. And in particular, that makes it difficult, at least using standard techniques, to optimize over it because it's a very complicated polytope. So what you could hope to do is the following. You could hope that you increase the dimension to some n, some big N, which is bigger than the little n. And in this increased dimension, you find this much simpler polytope. Okay, simple here is in terms of the number of facets. And then if you're clever enough, maybe you can show that this simple polytope it linearly projects to the much more complicated polytope in low dimensions. And then actually you would be in great shape because if you can optimize over this polytope, you can optimize over this polytope as well. So if there exists, say, a polytope with polynomially many facets that projects to the TSP polytope, then you would have a polynomial time algorithm for TSP. Okay? So this result shows that any polytope that projects to the TSP polytope has a size at least 2 to the root n. Okay? And actually, you can think of it equivalently as you take sort of the standard LP for TSP, and then you can add some more variables. Right? You can add a polynomial number of variables, and you hope that when you add these variables, the number of constraints you need to specify the polytope will drop dramatically. And it's not completely an academic discussion because, say, for spanning trees, it's known that the spanning tree polytope has actually exponentially many facets, and yet there is an extended formulation of size n cubed for spanning trees. So if you look at spanning trees on the complete graph, there is a way to add n cubed new variables to the basic linear program, so the number of constraints becomes polynomial. Okay, so that's this model here, and then recently, sort of these results were extended to show that approximating clique within n to the half minus epsilon requires linear programs of size 2 to the n to the epsilon, and then Braverman-Moitra got this actually now n to the 1 minus epsilon approximation requires 2 to the n to the epsilon. So what I want to stress is, first of all, you have very strong results in sort of for specific LPs, and somewhat weaker result for this very kind of beautiful general notion of an extended formulation. And here we actually, the lower bound examples are very sophisticated. They're random graphs or geometric constructions or things coming from extreme combinatorics. Here, this paper made this amazing discovery that basically the cut polytope contains inside it some matrix related to this set disjointness problem. And then actually that discovery was used in all 3 of these results. So sort of it's this singular point, you don't really know how to move out from there. So what we'd like to do today is sort of be able to prove these kind of strong lower bounds in this general framework. And then more than that, of course, it allows us now to use these very sophisticated constructions to argue here. So it sort of expands the class of examples we can use to talk about general linear programs. Okay, so now let's get to Yuval's question about what is a linear program. And I think it's a very satisfactory answer, but please, object if you feel like some moral urgings, like this is a travesty against humankind. Okay, so first, what is max cut? You have a graph and you have a subset, and then this function cut of S, this is the fraction of edges that cross the subset in the graph. Okay, remember that because this function will come up a lot in the talk. So cut G assigns to a set the fraction of edges crossing it, and then the max cut, the optimal value here is just the maximum over all the cuts of the cut value of the subset. Okay, so suppose we wanted to write down a linear program. What's the standard thing you do? First, you write down max cut as, say, a quadratic program. Okay, and then you say, well, I can't have products xi, xj in a linear program, so I'll linearize this by having some variable that represents this product. Okay, so for instance, here, suppose I want to introduce variables yij that represent 1 minus xi, xj over 2. Okay. Okay, so then the objective function becomes maximizing the sum of these yij's over all the edges. So okay, so this is sort of what one step in designing a linear program is linearizing your objective function. Okay, and then the second step is now that you have a linearized objective function, you need to have a polytope to optimize over, right? So okay, so now you can start adding in any inequalities that are true for your original integral variables. You can add them in. The most obvious one is that the yij should be between 0 and 1. You start to get more clever. You notice that on every triangle, A cut can cut at most 2 edges, so you throw those cuts into the LP. You notice that in every triangle, a cut can cut cannot cut exactly 1 edge, so you throw that into an LP, the LP. And then, of course, you can get, now you're on a roll, right? So now you say, oh, actually, for a 5 cycle, I can cut at most 4 of the edges, and you can keep going. And of course, the whole idea of these linear programming hierarchies or these extended formulations is to somehow automate this process so that it's not like every day we're wondering if you just add one more constraint, can you suddenly solve the problem much better? Okay, so this is the standard relaxation. Now, what do I mean by a linear program? I wanted to have 2 steps. The first one is a linearization of the objective function. So for every input size n, we are going to be working, we'll have some number m, which is the number of dimensions of the relaxation. And then we have the following. For every graph, we have a vector corresponding to the graph. For every cut, we have a vector corresponding to the cut. And then and this is the linearization. It should be that if I take the inner product of the graph vector with the cut vector, it's the cut value. Okay? This is what I mean by linearizing the objective function. Okay, so you can take any vectors you want, any for the graph, any vectors you want for the cut, but they should satisfy the fact that you actually get the correct thing on the integral solutions. And then you just need some polytope. And the requirement is that the polytope contains all the integral points. Okay, so that's a linear program. You have some vectors for graphs, some vectors for cuts, and a polytope specifying that contains all the integral points. Okay, and then the LP value is just the maximum over the polytope of the inner product with the graph, and the size of the relaxation is the number of inequalities you need to specify the polytope. So there's a number of facets of the polytope. Okay, so this is the model. It's a non-uniform model of computation because for every n you have a different possible relaxation, right? And I mean the real constraint here is that so if you think about it, what you can do is you think about the input graph is just the complete graph, and then later I give you the weights. So the real constraint here is that the polytope is not allowed to depend on the weights of the graph, right? It's not like I give you the graph and then the polytope can contain contain some inequalities depending on what weights you put there. Okay, but that's kind of what people mean by linear programming. Like you give me, I have a polytope, and then you give me the weights, and I optimize the weight function. Okay, okay. So this is what we mean by a linear program. Does anybody object or? Okay. I mean, in particular for like max CSPs, all the relaxations for LPs and SP people try to use, they look like this. Yeah.
Just make sure the polytope is the same for all graphs, right? This only depends on.
It only depends on the number of vertices. Yeah. Yeah. So you can think about the graph as just being the complete graph, and then the polytope is the same for all the weight functions you give me as input. Yeah, and this is necessary if you. Yeah.
This is a little bit of a divergence from what you're doing, but you could have an exponential size linear program with an implicit algorithm for solving it rapidly.
Yeah, so
column generation technique.
Right. So this doesn't rule out like ellipsoid having a separation oracle and using ellipsoid algorithm. This sort of kind of rules out interior point methods that depend on the number of facets, or as a combinatorial problem, just rules out the existence of these small relaxations. But this is true. So for the perfect matching problem, of course, we have a polynomial time algorithm based on an exponential size linear program that uses ellipsoid. And we don't know, it's still open whether or not there's a polynomial size linear program for matching. Non-bipartite matching.
Polytope, a polynomially representable polytope, or accessible polytope.
Yeah, right. Yeah, then things seem to get could get very, very hard. But so this doesn't rule out linear programming. For matching, we know an approach based on linear programming, even though we don't know of any small linear program. And in fact, Yanakakis conjecture there isn't any small linear program for matching. But we don't know the answer to that. Okay, so that's the notion of a linear program. What's the notion of approximation? We'll say that a relaxation is a CS approximation if whenever the max cut in the graph has value at most S, the linear program tells you that the value is at most C. Yeah.
Your last comment. So there seems to be an inherent weakness of this extended formulation method. That if you believe it, then problems that you know are easy is telling you are hard. So there is something
I mean,
We actually don't know. For a spanning tree, for instance.
We don't know, but the indications are that this is what's happening. So as a methodology, this is still, there still leaves something to be desired. Right?
Sure. We'll, you know, there will always be something to be desired, right? And you can make small steps.
Yes, I guess the issue is to make a model which doesn't capture P not equal to LP, and yet something.
Right, and this one, I mean, this extended formulations as projections of polytopes is just beautiful. The idea, right? I mean, that's okay. So it's a CS approximation. If whenever the optimal value is at most S, the LP can prove to you it's at most C. And what you should think of here for max cut is that in the hard instances, the graph will basically have S being about half plus epsilon. So every cut cuts only about half the edges. But the LP will try to claim that that graph is almost bipartite, that there's a cut cutting almost all the edges. That will give us factor 2 gap for max cut. Okay, so now how are we going to prove lower bounds? It seems like a very general model. Okay, we'll come back to this in a second. So the point is, Yannakakis gave this beautiful framework for proving lower bounds for extended formulations. So one thing you have to be willing to do is whenever you see a cut, you have to be willing to associate it with the corresponding Boolean vector. So I'm going to switch from talking about, this was a function on cuts. Now it's going to be a function on Boolean vectors where the cut is just the cut defined by everything which is equal to 1 and everything which is equal to minus 1. Okay. So now here's Yannakakis' characterization. If you have an LP relaxation of size R, that's a CS approximation, then you have these non-negative functions Q1 up to Q sub R on the hypercube, such that whenever the optimal value is at most S, there exists non-negative weights such that, okay, so this is an equality of functions. So by here, this function I mean C is the constant function. This is the function that assigns to cuts the fraction of edges across them. And then this is the sum of these functions. So what this is saying is that the LP is trying to prove that the value of the maximum cut is at most C. So this is saying the only way it can do this is first, before it finds out the graph, to give you these functions. And then it has to be that now for any graph, it can put the C minus the cut value into this cone spanned by the QRs. Right? So this is in particular a proof. Right? This equality constitutes a proof that the maximum cut value is at most C, because the right-hand value is non-negative. So it constitutes a proof that C minus cut is greater than or equal to 0. And the claim of the theorem is that actually this is the only kind of proof the LP can give. All right? And actually here's the proof of this. Take your linear program, so you maximize your objective function over some polytope with R constraints. And then what are the QIs? The QIs are just going to be the slack functions. So, okay, so I have a bunch of constraints. So now for the ith constraint, I define this function QI so we know that our polytope contains all the integral points. So for you can test for the ith constraint against the integral point corresponding to the cut S. You can look at how much slack is there. This is the function QI. QI is a function on the hypercube, but for consistency, I'm making a function on sets right here. In the next slide, the sets will go away. Everything will be functions on the hypercube. So now, what does Farkas' lemma tell us? It tells us that any linear inequality that's valid for this polytope has to be actually a non-negative linear combination of the inequalities that define the polytope. So if the LP has value at most C, then it means that this inequality is true. This is the same thing as saying the LP over the polytope P. And therefore, Farkas says that we can write this as a non-negative combination of these things. That exactly gives us a representation. Notice that if I put a cut vector here, then it's exactly C minus the cut value. So that exactly gives us our representation from the theorem. Okay, so this is just Farkas' lemma restated. And it's if and only if. It's really a characterization of when there exists a linear programming relaxation of size R. Okay. Okay. Good. So now I want to prove lower bounds against these things. So how does one prove a lower bound? Well, the LP gives me this cone of functions. So what do I need to do when I get it? Well, I need to find the graph G, and then I need to prove that this point is not in this cone. So I can do that with there's only one way to do it, by finding a separating hyperplane between the point and the cone. So this is the idea for the lower bound. The LP gives me these functions that give me this cone. Then I find a point outside and a hyperplane proving that the graph is not in this cone. Okay, and in fact, we're going to do it in a sort of special form. We'll find a so here I said H is the hyperplane. H is really the normal vector to the hyperplane. But we'll find an H such that the inner product with all the Qi's is greater than or equal to 0, and the inner product with C minus the cut function is less than 0. And then this will prove, that this equality cannot hold, right, just by taking inner products with both sides. Okay, so I want to stress two things here. First of all, right, H is just a function on the hypercube. Okay, I call it a hyperplane, but think about it as a function on the hypercube. And the second thing is, you notice that, I mean, if you look at this, there's no room for error here. This was 0 and this was 0, which always makes me, when I'm listening to a talk, uncomfortable, because I have no idea how people even start to prove equalities. But the point, so the point here is though that if you think about, suppose I have sort of some kind of setup like this. If I decrease the completeness value, so I'm trying to prove a lower bound, say where C is 1 minus epsilon. If I increase this to 1 minus 2 epsilon, then actually I can get some slack in this hyperplane. This inequality becomes more negative. So there will be some noise which starts to arise in the proof, and you can wonder, the noise seems to be bad for this kind of setup, but by borrowing a little from the completeness, we can always make the hyperplane a bit fatter. Okay. All right, so now I told you how we're going to prove a lower bound, and I said we're going to use the Shirley-Adams hierarchy. So what is Shirley-Adams? So in this setup, Shirley-Adams actually has a very beautiful, clean description. Here's a definition we've seen already. A function is a k-junta if the function depends on only k of its input coordinates. And now, Shirley-Adams for k rounds corresponds exactly to this setup where the functions can be any non-negative k-juntas. Okay, so in other words, Shirley-Adams for k rounds is a CS approximation if and only if so let's say Shirley-Adams for k rounds proves that the optimum is at most C, if and only if I can write this function as a non-negative combination of non-negative k-juntas. Okay, so actually at the sort of just how it's specified here, it's not clear. I could need quite a large number of juntas. I mean, right? It could be an infinite number of points in this cone that I need to use. One thing Shirley-Adams proved is that actually it suffices only to use n to the order k functions to do this to get this expression. But we don't need that. We'll just need the fact that Shirley-Adams corresponds to k-juntas, and I'll come back to that at the end. But sort of that's our starting point. Okay, so here's so now we're jumping into the proof. Okay.
Question.
Yeah.
That seems like a strengthening of Farkas's, or is it that general?
What do you mean?
So first Farkas gave that it's non-negative. You can write it as a non-negative combination of some fundamental inequalities. But now this seems to say, in fact...
Which part? This theorem?
Shirley-Adams allows you only to use this is it restricts you.
Yeah, so sure, and in fact it's equivalent. So the best sort of way that you can express things like this using, now I don't give you a bounded number of functions. You can use as many functions as you want, but your functions have to be local. So this is exactly equivalent to Shirley-Adams. Okay, so now we want to use a Shirley-Adams gap to prove a gap in general. So let's take G0 to be some gap instance. So the optimal value of G0 is at most S, but k rounds of Shirley-Adams thinks that the optimal value is bigger than C, right? So again, think about like this graph has max cut by about half, but Shirley-Adams claims that the graph has max cut near 1. Okay. So what do we know? We know from this that that there is a hyperplane separating this function corresponding to G0 from the cone of all the non-negative juntas. This is just what I said on the previous slide. So actually you can give this hyperplane explicitly, and we'll need to use a couple of properties of the hyperplane. We won't just be able to use its existence. But this is what we have to work with. We have a hyperplane that separates some hard graph G0 from all the non-negative k juntas. Okay, so let's say the size of G0 is m. And now what we're going to do is we want to like slowly build up the class of functions we can handle. At the moment, we can only prove lower bounds against non-negative k juntas. So we'll start building until we get to be able to prove lower bounds against all functions, against any small family of functions, and then we'll be done. Okay, so the first class I sort of want to extend to is let's go from k juntas to sort of things which are still very special but depend on many more coordinates, to n to the 0.2 juntas. Okay, So the way we're going to do that is kind of a commonly used method in things like this. We're going to take some graph G on n vertices where n is much bigger than m. So think about m as being about root n. And then each of these functions is a n to the point 2 junta. So let's say this is the set that Q1 depends on. This is the set that Q2 depends on, and so on. Okay. So we have all these sets that each Qi depends on. And then what we're going to do is just take this hard instance G0 on m vertices and randomly plant it in this big n vertex graph. Okay. So you have to think, well, that was a random planting of G0. Okay. So what do we expect will happen? G0 is size only root n. So when we randomly plant it, its intersection with these junta sets will become much smaller. In fact, for any one of the sets, the expected intersection has size less than 1. Okay? Right? Because the probability for any one of these influential coordinates to end in this set is only 1 over root n, and there are only n to the point 2 of them. Okay? And so, in fact, the probability that any fixed function has k coordinates in there, you just take a union bound, I've chosen the things correctly, is like n to the minus k, times n to the minus some constant times k. Which means that I can actually do this for up to n to the k functions. So if I set r to be n to the 0.3k, then I can actually find the random restriction such that every single one of the functions only depends on k coordinates in the random restriction set. Yeah.
So at this point you lost polynomial in the number of rounds?
No, this is perfect. The number of rounds is k, and the size is n to the order of k. So polynomial size corresponds to the constant number of rounds.
You increase the size of the graph, though, by a polynomial.
Yeah, yes, but that didn't lose. That didn't lose anything.
More later,
yeah, this is the.
Okay.
Right, there's a reason we only get n to the log n. It's not here. This step is tight. So, I mean, this step is tight up to polynomial factors. But it's. But this is where the connection between the number of rounds and the size comes from. It comes from this part right here, where now you see that you're looking at about n to the k functions, and you had k rounds of Shirley atoms. Okay, so the point is that, and by the way, the graph outside G0 is just disconnected, or just weight 0 everywhere else. There's nothing interesting happening except in G0. And now you can basically just transport this hyperplane down to this, 2 to the m dimensional subspace, and you prove a lower bound against these functions and using this graph. Okay, so this shows you that if your functions are all n to the point 2 juntas, then you can prove a lower bound against them. Okay, all right. Okay, so now how do we reduce to the case of n to the point 2 juntas? So the first thing we do is smooth out the functions. Okay, so this is the hypercube, and think about all the points x in the hypercube at which one of these functions is big, say at least r squared. Okay, so like. So this is okay. So these are all sort of the bad parts of the hypercube. Just by Markov's inequality. Okay, so I guess this is too much to go. Too many clicks, right? The lems are non-negative, so I can assume that the expectation of every function is 1, say, just by normalizing it. Okay. Right. So let's assume that the expectations of the functions are 1. Then, just by Markov's inequality, sort of for any fixed function, I can only be bigger than r squared on 1 over r squared fraction of the hypercube. So in fact, by Markov's inequality, the total measure of bad points for any function is, you take their union is only 1 over r. Okay, so it's a small fraction of the cube. So the point is that I'll just make the following promise. I'm going to produce this separating hyperplane, this functional h. At the end, after I produce it, I'll just zero out h on these few points. Okay, so then I can ignore them. And the reason this works, this is where we need to use one part of the Shirley Adams functional, is that it's a fairly smooth functional. It doesn't depend too much on any one point. So since the L infinity norm of the Shirley Adams functional is small, this is actually a very small amount of error, zeroing out on this small measure of points. Okay, so that's one. We'll use it one more place.
How do you get this fact? Like, you have to look at the CMM proof and stuff?
No. So I'll do it if like in the question period. If you ask, I'll write down explicitly what is the functional.
Okay.
So then you can just see that it's. But it doesn't use. This is all sort of works for any CSP. So we don't use the fact that. I mean, obviously we need to use the Charkar-Makarchev bounds eventually, but we don't need to know anything about how the gap instance is constructed. This is small just by read it. You read it off from Shirley Adams. Okay, so now we have our functions that satisfy this kind of L infinity bound. Now we want to prove some structural fact about them. We'd like to prove that every such function is well approximated by a junta. Then we'd be done, right? Because we prove lower bounds against n to the 0.2 juntas. Okay, that's way too much to ask, but here's what one can prove, and the proof is very simple. There exists, okay, it's a k times log r times n to the 0.2 junta. Think k is something small. Okay, k is even a constant for us. Okay, so basically, and log r is also small. So really, these things are much smaller than n to the 0.2. You should focus on n to the 0.2 here. This is an n to the 0.2 junta q prime, such that every low degree Fourier coefficient of q minus q prime is small. Okay, so q prime is a junta that approximates q. It approximates the low degree part of q. Okay, and not in a particularly strong way. It's you have a bound on every Fourier coefficient. I mean, note that there are like n to the k such Fourier coefficients, so this is not such a great bound. Okay, so you might be worried that you have this approximation. The high degree part of q minus q prime could be something crazy. Okay, so here's where we use the fact that we use another fact about the Charlie-Adams functional. It's actually only a degree k as a multilinear polynomial over the hypercube. Okay, in some sense, the Charlie-Adams only needs to fool things that look like integral distributions on subsets of k vertices. So sort of now you use its power against it. So if it can be expressed with just degree k. So it's kind of like the lowly Charlie-Adams functional is here. And q minus q prime could be quite large in the high degree part, but it kind of goes over his head. Right? So sort of he can't, basically the high degree part of q minus q prime is orthogonal to h. So you don't have any bound on it. This was a more interesting meme when it was animated, but I couldn't do it. Okay. All right. Wait, okay, yeah, so that's the proof. Let me just recap. So here's the basic idea again. By zeroing out this, whatever function we get, by zeroing it out, we can assume that all the functions are, by zeroing out on some small measure of the space, we can assume that all the functions are bounded. Now, every such bounded function can be approximated by an n to the 0.2 junta in the low degree sense. So the low degree part of qi and qi prime are small. Then we do this random restriction. Now, every qi prime depended on n to the 0.2 coordinates. But when we do this, sort of when we randomly plant this graph G, each qi prime only depends on k coordinates in G. And then, okay, so now the Charlie-Adams functional can fool these qi primes restricted to G0 because they're only k juntas. But now, according to the Charlie-Adams functional, it appears that qi and qi prime are very close together because they're close in the low degree sense, and this functional can only perceive low degree things, right? It's orthogonal to all the high degree part. Okay, so that's the end of the proof. Okay. Are there any questions? Okay, so if I have time, I'll say what the function. Yeah.
Does this work for a specific value of S?
So this works for whatever values of CNS you get from Charlie-Adams. So for max cut, the gap is between 1.5. For 3-sat, the gap is between 1 and 7/8. Right? I mean, it works for any CNS. You take a Charlie-Adams gap instance, you get a gap instance here.
Can you say why it's enough? You only know that the individual coefficients are small. Can you say why it is enough to fool?
Okay, so let's just make sure to ask me that in a second. Okay. So I mean, I'm ending quite early, so there's plenty of time. So this is the answer to this question is why we cannot. So for Charlie-Adams, you know that actually there's a lower bound against n to the epsilon rounds. Why can't we prove lower bound against 2 to the n to the epsilon size linear programs? It's because of addressing this issue. So that's where the problem comes. Okay, so let me, maybe even the most exciting part of this is the future directions. Okay, so one of them is to handle this problem. It seems to be basically just a technical weakness on our part that we cannot go push it all the way to that we cannot get this dependence to hold for k arbitrary. We can only get this connection to hold for k being about log n, for up to log n rounds. And then afterwards our proof breaks down, but the connection should keep holding. It should be that you can prove sub-exponential lower bounds against all of these things as well, not just super polynomial. there's a very interesting question of whether this can be extended beyond constraint satisfaction problems, like to TSP or to vertex cover. So the big thing we use about constraint satisfaction is that the assignment space is a product structure. We can do Fourier analysis there. The second you go to some other problems where you don't have a product, like take the uniform distribution on TSP towards on the complete graph. That's a very interesting combinatorial object, but it doesn't have a product structure, and so things like junta have to be defined more carefully, and it's not clear what happens. Okay. Can this be used to resolve this original problem of Yanakakis on the size of linear programs for the perfect matching polytope? So Yanakakis proved that any symmetric linear program for perfect matching has exponential size, but generalizing this to arbitrary linear programs has been open since his paper.
This was not done by this groups of people?
No. So their thing only works for TSP. It doesn't work for perfect matching.
And this perfect matching for non-bipartite graphs?
Yeah. For bipartite graphs, you have a polynomial size. There's a flow relaxation, right? So you can write it as flow, and you get polynomial size. Their technique actually proves that, for instance, independent set cannot be solved exactly with small linear programs, and then they use an NP hardness reduction to TSP to get the polytope for TSP. So it will not work for matching. But I mean, Shirali-Adams for perfect matching is quite well understood. So there's a paper of Claire Mathieu and Alistair, which sort of analyzes very tightly the gap for perfect matchings all the way up to the maximum number of rounds. So you have Shirali-Adams gaps here. The question is, can you use this technology to prove general? I don't know. And then, of course, after you see there's some connection between linear programs and Shirali-Adams, you want to do something similar between semi-definite programs and the Lasserre hierarchy. In particular, the techniques for TSP, the recent techniques developed for TSP, they cannot work for semi-definite programs because, as I said, they're based on this sort of basically one hard matrix, and that matrix is not hard for semi-definite programs. Okay, whatever it means, it's easy. That matrix can be easily figured out by semi-definite programs. So, but this gives a path, possibly a difficult path, to proving lower bounds against arbitrary polynomial size semi-definite programs via the strong gaps we know for Lasserre. Okay, let me stop there. Okay. Yeah. So first, Elchanan's question was about. So we only know that we know that the degree of K Fourier coefficients of the. Okay. Yeah.
Maybe Ryan's question will lead to an answer to Elchanan's question.
Right. So maybe I think I can answer Elchanan's question without doing anything, and then I can. So I'm going in the sort of simplest too. So we know that the degree K Fourier coefficients of this are at most n to the minus 0.1. So the immediate problem you have, these are functions on n bits, so they have n to the k Fourier coefficients. So if you just applied, if you just calculate the L2 bound, even the low degree part of this could have a huge L2 mass. That's problematic. But the key is that we do this random restriction to this set of size m. So actually only the Fourier coefficients in m matter. Everything else outside goes away because the functional only depends on things in m. So then you get something which looks like m to the d times n to the minus 0.1. And now if you choose these parameters appropriately, you can get this to go to 0. Oh, sorry, k. K is number of rounds. Sorry, k is so k is the degree. So if we look at this thing we have only m to the k Fourier coefficients, and then we can just use an easy bound here. Okay. So now if you choose m to be n to the 1 over k, then you can make this little o of 1 appropriately. This is also, in order for this to be little o of 1, you see that this means that you can only go for about log n over log n rounds before this dies. So sort of like our inability to do something non-trivial here is what makes the number of rounds stop. Okay. Okay. And now Ryan's question. Okay. So what does for people who maybe are not familiar, what does Shirali-Adams do? Shirali-Adams just insists that your linear programming solution, when you restrict it to any set of k variables, the induced solution on those k variables can be written as a convex combination of integral solutions. So it insists that for every small set of variables, it really looks integral. So there's a different way you can do this setup. So you can think about Shirali atoms as giving you sort of this pseudo expectation. So basically, it has the ability on anything that.
James,
Yeah.
Can you just say you referred to the Shirali atoms operator? Can you just? I understand the description, but what's the operator? Yeah.
Oh, the functional. Yeah. We're going to write down the functional now. Okay. So if you think about what this means, it means that for any function that depends on only k coordinates, I can talk about averages of this function under this purported distribution that actually it's a real distribution that Shirali atoms is giving me. So this gives us ability. This sort of this notation came from this B and who's the last author on the paper? Z. B, Z with some authors in between. Yeah, Brandau, Harrow, Barak, Storer, and and Kellner. Yeah. So see, it was better to do Elkman's thing and just say B to Z. For Lasserre, okay, so you can think about this kind of pseudo expectation, which to any function that depends on only k coordinates assigns a value that's an average over some distribution. Okay, so this will be okay. So based on it actually you have more than that. You have the property that if you look at any two of these distributions and you look at what they induce on the intersection of those things, then there's some consistency. Okay, so what it means is you can define this functional on degree at most k multilinear polynomials. So it's a linear functional, and it has the property that the expectation of a polynomial is greater than equal to 0 if p itself is greater than equal to 0 and depends on only at most k coordinates. Okay, so you can think about all such operators. They map degree k multilinear polynomials to real numbers. They're linear functionals, and they can prove that anything that depends on only k coordinates and is non-negative is actually non-negative. And then you can think about the Shirali atoms value after k rounds on a graph G. Let's just look at max cut. So this is the maximum over all such pseudo expectation functionals of the expected LP value. So for max cut, it's like some I over j 1 minus pseudo expectation xi xj over 2. So this is equivalent to k rounds of Shirali atoms. You maximize over all of these pseudo expectations of just the pseudo expectation of the objective value. Okay. So now, what is the functional? The functional is just this. Sum over all subsets of size k. Look at the where the chi alphas are the Fourier basis. So this is the functional. It's the okay and the one and the okay so and the point is that all right let's see one thing. So okay, what is this functional depends on only it's only degree k, so it satisfies one of the properties I said. Each of the Fourier coefficients is at most 1 because it's just some pseudo expectation of something that depends on only k variables. Well, okay. Yeah, each of the Fourier coefficients is at most 1. So in particular, the L infinity norm of this function is at most m to the k. Right? This is not the greatest bound on the L infinity norm, but we're throwing these things around anyway. So the one thing you might want to see is why does this thing fool juntas? Okay, and the reason is just because if I take if Q is a k junta, then the inner product of H and Q is just equal. Okay, Q is a non-negative k junta. The inner product between H and Q is just equal to some expectation over a real distribution of Q, which is obviously greater than or equal to 0. because q is a non-negative value. So the point is that the inner product, for any function depending on only k coordinates, the inner product with h is some expectation over the input bits. And so it's always non-negative. Okay? So this gives you the property that for any k junta you have this non-negative inner product. And now if you look at the, if, so now look at the cut function. If Shirali Adams claims that it has an LP value which is bigger than C, then okay, you need, this is the okay, and you need to just notice that this is this is the expectation of a constant, which is a constant. That's good. So if Shirali Adams claims that the value is bigger than C, then this is less than 0, and for every junta is greater than equal to 0. So that gives you your separating functional for juntas, and then you can follow through the rest of them.
Somehow realized that the CMM lower bounds for Shirali Adams for cut stop at like n to the epsilon. I think it's possible that with like root n rounds of Shirali Adams you can beat a half.
It's a good question. Maybe.
Just asking you to
no.
guess.
It just happens that that Luca actually has some the algorithm that can do this on. Let's see. I'll tell you the. It seems that root n might be the right value. Like it seems possible that you could do it with root n rounds. That you could get something better than half versus 1. I can tell you why offline, but it's birthday paradox. Okay.
It's time.
We'll meet again at 10:15.